Hello, my name is Simone Honori, and I'm a faculty in the Department of Energy Resources Engineering at Stanford University, where I also lead the Stanford Energy Control Lab. And today, together with my PhD student, Kevin Moy, we're going to talk about characterization of energy storage duty cycles for grid application. I will go over some of the motivations behind this work and discuss the main research objectives. Kevin will then cover some of the works that have been found from the literature that discuss basically how duty cycles for batteries have been synthesized. And he will then go on and explain the algorithm that he developed for characterizing dispatch profiles. And he will show you results related to the characteristic duty cycles and synthetic duty cycles that are going to be then in the next future use for experimental work. And he will wrap up this presentation by discussing some concluding remarks. At the end of 2017, global renewable generation capacity amounted to 2,000 gigawatt, of which half were from pumped hydro and wind and solar to follow. The renewable energy in California landscape looks is summarized in this chart, and this plot shows the renewable generation from power facilities serving California load from 1983 through 2018 by resource type, which include behind the meter solar, wind, geothermal, small hydro, and the biomass. The current goal requires 33% of retail sales from renewable resources by 2020, and according to those estimates, that goal has been already passed and reached and passed, and California is on the right direction to meet the 60% goal by 2030. And such a rapidly evolving energy landscape and aggressive carbon reduction goals are indeed posing new challenges to the grid, and are therefore increasing also the need for energy storage technologies. Both wind and solar generation are intermittent, and energy storage systems are required for grid services. Now, energy storage is not some monolithic application. There is a lot of different types of energy storage, and besides pumped storage hydro, which dominates basically the landscape, and which is not included in this chart, we see that there is a quite wide range of options there, going from sulfur battery, lithium-ion, lead-acid, flow batteries, and so forth. And according to the Energy Storage Technology and Cost Characterization Report issued by the Department of Energy in 2019, lithium-ion batteries basically have the majority of share, with almost 50% of the total energy storage deployed. Energy storage technologies are very fascinating and interesting topic. And one of the things that we learn about those technologies, that they vary greatly in both discharge duration and power output. output. And to summarize these characteristics, we have here a chart that I borrow from EPRI, where electrochemical, electrical, and also the types of energy storage are plotted and compared and related to each other in terms of max discharge time and power. Pumped hydro and compressed air energy storage are also referred to bulk energy storage because they can provide long-term energy. They can store larger amount of energy, especially when compared to batteries. And they are of the size of the order of gigawatts. On the other hand, batteries basically can provide loads for a duration of minutes or hours. So, and each energy storage devices are two main attributes that needs to be understood before we place them in a particular application. And those are output power, and energy. And those are related, but they're not interdependent. So a battery might, for example, required to deliver high power for short period of time, giving low energy. On the other hand, you might also have some sort of low power requirement for long period of time. So understanding those characteristics, the attributes, is very important before we place them in a particular application within the grid. Available technologies in terms of electrochemical energy storage technologies include lead-acid batteries, lithium-ion batteries, and flow batteries. Lead-acid batteries are mature technology. They suffer from low cycle life, but they are well known for their recycling credentials. Lithium-ion batteries, on the other hand, they are becoming increasingly popular, mostly due to the higher energy density and the widespread use in consumer electronics and also in the transportation markets. Compared to lead-acid batteries, they are less safe due to the organic liquid electrolyte that they use, which can burn readily when ignited. And from a recycling standpoint, they also it's also not clear what is the recycling route of this technology at this point, and as ongoing research is being done on this topic. So, of the electrochemical energy storage technologies in place since 2003, nearly 80% is provided by lithium-ion batteries. And indeed, they are considered the best means to store energy in grid application. That's why we're going to focus on lithium-ion batteries to provide the energy needed in the grid. So when we talk about lithium-ion batteries, we often think of electric vehicles. And so the revolution that is happening in the power system sector, thanks to more renewable penetration and new energy storage means to save and store energy, such a revolution is happening at the time where also the transportation sector is going through a profound transformation. And that is, through the electric vehicles, which are possible thanks to lithium-ion batteries, in fact. So the transportation sector is transitioning basically from systems that are powered by petroleum to significant uptake of EVs. And predictions done by researchers at Bloomberg show that by 2040, EVs will account for 35% of all new vehicle sales. And the turning point, basically the year when the electric car sales are predicted to surpass internal combustion vehicles is 2037. So indeed, the transportation electricity markets are increasingly linked, and they will be even more in the next decades. The reduced battery cost indeed has been the main reason as to behind the high adoption of such energy storage technology. And so when we think about grid, people are very often talk about secondary life of batteries and how to use retired EV batteries for grid applications as opposed to new batteries. So there is new opportunity in this domain to understand whether or not repurposing batteries in electric vehicles to serve the grid makes sense. And so that's also what we are interested in, and in particular we want to try to quantify what's the remaining useful life in those batteries that go from serving EV applications to grid storage now, and so we want to do this through modeling and simulation tools, and we want to use those tools to understand how energy storage performs as a long-term resource. We have learned as we worked with automotive batteries, we learned that performance, long-term duration of those systems is directly connected to how we use them. Okay, so degradation trajectories are usage dependent. And so if that is the case, the question about how long a battery will last when used in grid application will really depends on how you're going to use it. And to define how we're going to use it, we introduce this concept of duty cycle. A duty cycle is a charge and discharge profile, oftentimes given in terms of power, but sometimes also in current. And what this represents is the demand associated with a specific grid application. And so each grid application has different duty cycling characteristics, and different cycling characteristics can lead to different capacity fade trends in batteries. Now, to predict the overall usage and the performance over the years, people use tools like capacity expansion models and things of this sort. So these are grid planning models. In those frameworks, the battery is seen as a bucket of electrons, and the only information that is provided is how much charge is in the battery at a given point in time. There is no information whatsoever about how the battery reacts to different temperature, different loads, and so forth. On the other hand, for real-time control models, people are using empirical models, oftentimes given in terms of equivalent circuit models. And in those equivalent circuit models, those parameters here are not known and needs to be calibrated. So, and this calibration is chemistry dependent and is usage dependent. So the duty cycle will define numerical values of these parameters, and they also depends on an aging and so forth. So so the problem with these two type of modeling approach is that empirical model could be since depends highly depends on the calibration, that you're gonna do on those models, the behavior of the battery cannot be extrapolated outside the operating conditions representing the data used for calibration. And so they can be, their accuracy can be very poor in certain, under certain operations. And they could therefore making operated battery manner detrimental to its health. And on the other hand, the grid planning models, such as they are oversimplistic, and they could be overestimating the long-term capacity of the batteries, for example. So what we are doing in our in this project with the students is to propose physics-based battery models. Those are electrochemical based models where we look at the concentration of lithium in the electrodes, and we model the fundamental relationship, the conservation of mass and charge within the battery. And those physics-based models that we want to build are going to be identified for secondary usage of battery. Before we do that, on the other hand, there are some other questions that needs to be answered and addressed. And the main one being, what is the impact of a characteristic battery duty cycle on model development? How does the duty cycle affect the, the tuning, the calibration of such a models? And this is a very important question, because we want to be able to then use those physics-based models to understand what is the most suitable chemistry for grid storage applications. There are a few options out there, like using NMC batteries versus as opposed to NCA or LFP. And so having highly predictive, well-calibrated physics-based model will help us to really, match the best way we can application and the type of energy storage technologies. And after all, our main goal is to really develop those high fidelity tools to provide guidelines for grid storage technology and application, especially when it comes to carry out prediction over a long period of time. Usually batteries in electric vehicles is meant to last 8 to 10 years, but when the installation of energy storage technology is done in a grid application, the expectation is for the system to last up to 20 years, or sometimes even more. So our approach is to we start from a yearly dispatch profile, so something that looks like something like this. So we have power versus time, and the time is 1 year of data. And this profile is very nice. It's very it's really not much we can gather from that. And so what Kevin has done is to develop an algorithm that is based on principal component analysis and k-means to really rationalize it. So we go from 1 year long profile to a 24-hour profile that contains the main information according to certain criterion that it will explain. And from this duty cycle analysis and the creation of the synthetic profile, we're going to go ahead and start the experiments using different chemistry, and the data collected from the experiments will add to the calibration of physics-based model. I understand that we then use for long-term prediction. So now Kevin will take over and he will explain the algorithm.
Hello, this is Kevin Moy. I will be leading the second half of our presentation. To start, here are some typical examples of studies of synthetic duty cycles for grid storage from the literature shown below. The first two papers by Schoenwald et al. And Ferreira et al. Were part of a larger project that was conducted for the United States Department of Energy. while the last paper, by Stroh et al., was published by Aalborg University. All of these approaches focused on creating and testing synthetic duty cycles for different grid applications, but without a systematic approach to characterizing the duty cycling. In these cases, synthetic duty cycles were either obtained directly from PV generation profiles, abstracted into constant charge discharge cycles, or are a result of some assumed control methodology. In contrast, we wish to obtain a method that can provide a thorough characterization of the grid application duty cycle directly from the usage of the battery within a grid application, as well as provide a means for synthetic duty cycles for further research. Next, the methodology. We first consider the duty cycling of a battery under the grid application of peak shaving. In this application, the goal is to reduce the utility bill charges, which are based on the peak consumption of power from the utility distribution grid by the load. There are many different methods to do this, including load reduction, adding generating resources such as solar and wind, and for our purposes, adding energy storage, which can charge and discharge to offset the peak load power. We now present the algorithm we developed for characterizing the dispatch, charge and discharge of the battery. We begin with the yearly dispatch, which describes the power output of the battery measured hourly over 1 year. Positive power indicates discharging, and negative power indicates charging. From this, we calculate the state of energy, SOE, and find the outdoor temperature, T, over the year. Then, we perform principal component analysis, considering each day of dispatch when the battery is actively dispatching. We compute metrics for this daily dispatch, and then project these metrics along their principal components to obtain a reduced subspace representation of the daily dispatch. Finally, within this subspace, we perform k-means clustering. Within the subspace, we find the days closest to the center of each cluster as representative days of each cluster. Then, referring back to the yearly dispatch, we find the dispatch of these representative days. These then represent the characteristic duty cycles of the yearly dispatch. This methodology uses PCA for matrix decomposition and unsupervised learning via k-means clustering to characterize the dispatch into duty cycles. We use this method as PCA has been shown to improve the performance of k-means clustering. Ding and He previously showed that principal components are the continuous solutions to the discrete cluster membership indicators for k-means clustering. We now present the algorithm in detail. The first step is to compute metrics for each day of dispatch. We select the 12 metrics shown. These metrics are selected to reflect the content of the dispatch, characterizing the power and frequency components of the dispatch, as well as the SOE and temperature while the battery is actively dispatching. We compute these metrics on charging and discharging separately, as different degradation mechanisms are relevant during each. We compute these for all days of dispatch to form the daily dispatch matrix, capital M. This matrix is shown at right, showing the variation of each metric for each day of dispatch. Next, we run PCA on this matrix M. We obtain the principal components and their corresponding eigenvalues, ordered from largest to smallest. We want to find the number of principal components, and therefore the dimension of the PCA subspace, P star. This is found using the equation shown, where we find the minimum number of components needed to reach 90% of the variance explained. This can be shown with the following plot, where, starting with the first and largest principal component, we add successive components until the threshold of 90% of variance explained is reached. In this example, P star is 5, so we use 5 principal components for the remainder of the algorithm. Now, we project the matrix M onto the PCA subspace, formed from the first P star principal components. In our example, P star equals 5. We therefore multiply the matrix M by the first 5 principal components in order to obtain the PCA subspace, capital P, of dimension 5. By using PCA, we also obtain an additional output towards characterizing the dispatch. Recall the 12 metrics computed for each day of dispatch, shown here. Now, in our example, the first 5 principal components are shown at right. We can use the magnitude of each metric within each component as its contribution to that component. For example, in principal component 1, the peak charge power contributes the most. And in principal component 2, the peak charging frequency contributes most. As principal components 1 and 2 explain over 70% of the variance of this dispatch, the peak charge power and peak charging frequency are important metrics for characterizing this grid storage dispatch. Now, we focus on the k-means clustering section of the algorithm. We need to determine the number of clusters used, NC. Given the representation of the daily dispatch metrics in the PCA subspace P, k-means clustering will assign each day a cluster. K-means clustering also finds the center of each cluster, termed the cluster centroid. This is shown in the plot below, in a case where P star equals 2, with cluster centroids marked as X's. We would consider this to be a good clustering output on P. This is because the dist within, or the maximum spread within each cluster, is small, and the dist between, or the minimum distance between each cluster, is large. In contrast, at right, we show an example of bad clustering output on P. This is because the dist within, again, the maximum spread within each cluster, is large, and the dist between, or the minimum distance between each cluster, is small. We therefore select the optimal number of clusters, NC, to balance both of these aspects, so that the distance between clusters far outweighs the spread within clusters. In this example, we choose NC to equal 2. Finally, we can obtain the characteristic duty cycles of the grid storage dispatch. First, in step 1, we perform k-means clustering in P, using the optimal number of clusters, NC, and find the corresponding cluster centroids. This is shown below for our example, where NC is 2. In step 2, we find the data that is closest to each cluster centroid. In our example, cluster centroid 1 is closest to the row of P corresponding to May 15th. And cluster centroid 2 is closest to the row of P corresponding to September 15th. Next, we refer back to the yearly dispatch and find the dispatch of each day found in step 2, as shown here. Finally, in step 4, we use all of these daily dispatches as the characteristic duty cycle of the grid storage yearly dispatch. We now present the results of this algorithm applied to peak shaving dispatch, and present an approach to creating synthetic duty cycles from the characteristic duty cycles. Shown here are the characteristic duty cycles obtained from peak shaving, conducted by the same 200 kilowatt, 400 kilowatt hour battery on 2 different loads, large office new and supermarket new. We can see that the characteristic duty cycles obtained are short, having characterized the entire year by only a few days worth of dispatch. They are distinct, both within and across different yearly dispatches. For example, We note that within the large office new duty cycles, that duty cycle 2 contains a large spike in charging, while duty cycle 1 does not. Both of these are distinct from all of the supermarket new duty cycles. On the other hand, all of these duty cycles are similar and indicative of the behavior of the dispatch under the grid application. In this case, the dispatch under peak shaving charges the battery immediately before discharging to reduce the peaks. Understanding this dispatch behavior is important for designing battery management systems, as it reveals the excitation of the battery under this grid application. This knowledge can also be useful for electric utilities to further develop grid applications and rate tariffs for battery energy storage. These characteristic duty cycles can be used to form synthetic duty cycles. The example of the large office new peak shaving dispatch is shown below. From these characteristic duty cycles, we can form two different synthetic duty cycles. The synthetic duty cycle at top simply concatenates the characteristic duty cycles. This could be used for testing both calendar and cycle life of a battery under peak shaving by including the inactive periods of zero dispatch. Alternatively, by removing these inactive periods, we obtain the synthetic duty cycle at bottom. This can be used for testing which focuses more on the cycle life of a battery under peak shaving, using only the active dispatch. In conclusion, we find that this combined PCA K-means algorithm allows for characterization of grid storage applications. This characterization only depends on the dispatch of the grid storage and the temperature of the system, meaning that it is independent of both the technology and grid application. This method is adaptable and customizable, depending on the metrics included and aspects of the dispatch desired. We also demonstrated that this characterization allows for the creation of synthetic duty cycles. Future work includes in using these synthetic duty cycles for laboratory testing and parameter estimation for grid storage physics-based models, with a particular focus on second life electric vehicle batteries. We can also apply this algorithm to additional grid storage applications, such as energy arbitrage or solar PV firming. We can thus build out a library of duty cycles for grid storage applications to be used for further analysis and testing. Finally, we would like to thank the Stanford Bits and Watts Initiative for their financial support. We would also like to thank Dr. Stephen Harris of LBL for his substantial contributions and insightful discussions on this research. This concludes our presentation. Thank you.